Eric has already been here?
Yep.
Oh, there you are. And you know how to run this? Yes. And then a lot of them do gravitational waves. 4 or 5 years. Yeah. And solar revolution. Okay. Oh yeah. That's going to be a major factor.
Okay, is everyone here? Yes. All right. So this is our second kind of grab bag session on kind of high energy astrophysical phenomena. And to kick off this session is Tdes, who is a second-year Einstein Fellow at MIT. So Tdes, please take it away.
Okay. This is good? Get better? Maybe I should put it up further. All right. Okay. Yes. So thank you very much for all of you for being here, and thank you to the organizers for arranging this symposium. It's really been a lot of fun hearing this amazing diversity of science that all the fellows are doing. Like I said, on Monday morning, I am a time domain astronomer. I work on finding transients and characterizing them across the electromagnetic spectrum. And what I'll be focusing on today is all of the new surprises and results that we are finding from essentially mining an existing data set from a survey that has been around for more than a decade. But what we've done is essentially reimagined the data products in a way that we've tailored it primarily for time domain science and how we could use it to find transients and go after lots of interesting questions that remain unresolved in stellar astrophysics. So a lot of this work would not have been possible without my amazing collaborators. I've tried to list over here. And for those of you who were around on Monday morning during the introduction, I understand that you're all very excited. You're waiting for this session, so we finally get to know about all of the things that go boom in the sky. All right. So scientifically, what I'm most interested in are stars and stars that are in binary systems. So for isolated stars, let's say you had a star with a mass m1. It started off with a mass m1. We understand the evolution of the star relatively well, such that once it runs out of hydrogen in its core, it expands, it expels out of all of its outer layers, either in a red giant phase, AGB phase, or a supergiant phase, and eventually as a supernova, depending on the mass of the star. And finally, what it leaves behind is a compact remnant, which is the properties of which is a function of the mass and the composition of the star. So, and this is relatively well understood for isolated stars. But what I wanted to emphasize for this talk is that things get much more interesting once you have binary stars. So imagine you had the same star, but now you have a binary companion. Here I'm showing a main sequence star, but for all you know, it could be a planet, it could be a supermassive black hole, it doesn't matter. You get all kinds of interesting phenomena across this parameter space in mass ratios. And as you can imagine, even if the stars were not quite talking to each other over most of their lives, once they start going towards their final fate, as these stars evolve off the main sequence, they will start talking to each other because of the presence of the binary companion. And that's when you start seeing a lot of the interesting physics, all the way from accretion, outflows, mergers, everything. And one particular phase that I will be talking about primarily today is mass transfer, and how we can actually use time domain surveys to study both stable and unstable mass transfer. Unstable mass transfer is really the difficult part to model and to observe, and how the infrared surveys are becoming particularly powerful at doing this. So what I'll talk about is this new infrared time domain dataset that we've started mining, which holds clues to a lot of the uncertain processes in binary stellar evolution that have to do with unstable mass transfer. And the specific mission that you may have heard of is the WISE mission. So WISE is a space satellite that was launched in 2010. It's been observing the sky very much like what you see over here. It has this orbit, and it takes images of the mid-infrared sky again and again. And it's been doing this for the last 12 years. And what you'd get with a survey like this is that you can create very deep maps. As you stack these images across years, you can create very deep maps of the entire sky in the mid-infrared bands. And WISE has been really the unique data set that does this. But what we wanted to do is that, say, hey, we are getting so many images that are time resolved. Why don't, instead of adding the images, why don't you just change the sign in the arithmetic and start subtracting images? And that's when you start finding transients. So this is how a typical transient discovery works. You have an image that was taken by WISE, let's say in one epoch. You compare it to another image that was taken maybe 5 years ago, and you subtract the two, you see something sticks out. And that's how we find transients. So it turns out that when you do this exercise on the entire WISE dataset over the last decade, there are a sample of 15 million transients, most of which have no optical counterparts, that are essentially lying in there. And this is a completely new phase space when it comes to infrared time domain phenomena. And we're now actually beginning to mine this dataset to answer very specific questions in the life cycles of stars that are in binaries. And that's what I want to go over for the rest of this talk. All right. So what I'll do for the rest of this talk is take you on this journey, which spans this entire dynamic range in mass ratios for binaries, all the way going from your usual Q of 1 stellar mass binaries to things that have mass ratios of 1,000 to mass ratios of 1,000,000. And there are lots of interesting phenomena that go across this phase space. And we start with the most common objects, things that are binaries. So stars that are in binaries, the mass ratios of order unity. And we know that these systems are very common. About 50% of sun-like stars are in binaries. That fraction only goes up to more than 100% once you go to massive stars. So we know that when stars are in binaries, they interact with each other, they undergo mass transfer. In a lot of cases, they undergo unstable mass transfer of the kind that we can see as dynamic phenomena in time domain surveys. The specific phase that I'll be talking about are mergers of stars, which remain very poorly understood. This is what we've often read in the literature as the common envelope phase. When two stars undergo mass transfer that is unstable, they enter into this common envelope phase, and many of them merge. And we know this happens in the universe because we see that directly. So here what you're seeing is a famous example of a merger that was observed in our own galaxy. You see, this is a binary system that started off as a binary that had two stars. Eventually, the stars came close together enough that they eventually merged and produced this spectacular eruption that we saw in our own Milky Way about 15 years ago. And when that happens, what you get is an eruption of the kind that you see on the right. This is an actual Hubble time-lapse image of a stellar merger called V838 Mon. What I'd like to highlight is that as this eruption happens, what this produces is a very cold outflow that's very dusty, and it results in this transient that's very red. You can see it visually. It's extremely red. So it primarily becomes an infrared-dominated phenomenon. The rates of these things are uncertain, but our best guess is of the order of 1 per year in the Milky Way, despite the fact that the last merger that was seen in the Milky Way was 15 years ago. And that obviously raises the question, where are the rest of the mergers in the Milky Way? And one of the ways to answer that is to go and look for them where they're the brightest, in the infrared. And that's what the WISE dataset allows us to do. So what we've been doing is to look for extremely red eruptions going off in the Milky Way plane. And when you start looking for these in the WISE dataset, you do find way too many of them. So here are examples of light curves from WISE of stars that have brightened by a factor of hundreds to thousands in the mid-infrared over the last decade. Red is W2, which is the 4.5 micron band, and black is the 3.4 micron band. You see these videos. These videos are actually images from WISE that show these stars they become so bright that they saturate the detector in WISE. That's how bright they get in the mid-infrared, because these are Milky Way sources. So we now have this sample of the order of dozens of things that look like stellar mergers that have gone off in the Milky Way. Probably not all of them are stellar mergers, but we have started doing this spectroscopic campaign from the ground where we go and take spectra of these things using the largest telescopes in the near infrared. And what we see is actually things that look like mergers. What you see here are examples of near infrared spectra that show the characteristic absorption features that we are looking for. These look like M stars in the near infrared. They have very cold photospheres, which is what we expect to see in stellar mergers. They become very red very quickly as they form dust, and their luminosities are insane. These are few thousand solar luminosities in the mid-infrared. They've all gone unnoticed in the optical bands, but they're some of the brightest infrared transients going off in the Milky Way all the time. We just don't see them because we're not paying attention to the infrared. All right. So with that, I want to take you a step further and to go to an interesting parameter space where you go to mass ratios of the order of 1,000. And then you might ask, what kinds of binaries have mass ratios of the order of 1,000? And then the one that I'd like to highlight is that if you have a star that's actually engulfing a planet next to it, then you have mass ratios of the order of 1,000. So we know that this must happen. We know of plenty of these planets that orbit very close to their host stars. The Earth has a similar fate eventually. And there are many people in this room who are much experts compared to me when it comes to hot Jupiters and their populations. But what we can expect to see in these engulfment events is the idea that what you're seeing is essentially a scaled down version of a stellar merger, where you have a star that's running not into a star next to it, but a planet. So the predictions have been around for quite some time that these should be happening in the Milky Way. And when you go and start looking for these again in the infrared data set, you do start finding them. So here is an example from a paper that we just submitted, where what you see is this bright mid-infrared transient that went off in the disk of the Milky Way. It has this short-lived optical outburst. And when you compare the properties of this object to the other red nova, it looks exactly like a red nova, except it's a factor of 1,000 lower in luminosity. It's going off in the Milky Way disk. And the best way to explain that is that what you have is a star that's engulfing a planet next to it rather than another star. And this really is exciting because we expect to see these things going off in the Milky Way. And what we have now, because I'm at the Space Telescope Science Institute, what we can do now, because we have events like this, is that we can actually go and look for what the signatures of the remnant look like. So it happens to be the case that we did get a JWST spectrum of the remnant of this eruption just last week. What you see here is the acquisition image from JWST. This is a mid-infrared. This is the MIRI instrument with the low-resolution spectrograph, where you see the sources clearly detected. So we now have actual chemical measurements of. We are working very hard. My collaborators are working really hard to get this data, but I think we're off to a good start because one, we got the correct target in the slit, which is a good start. And second, that the SNR is better than expected. So I think we're off to a good start. If you know how to reduce this data, please get in touch with us. We're trying to figure this out. Thank you. All right. So in the last part of this talk, I think what I wanted to go towards is, the most extreme events. Once you go to mass ratios of the order of 1 million. And then you're going into very interesting territory because then you're looking at things that are off in mass by a factor of 1 million. And then you might ask what lives in that phase space. And the ones that I'll be talking about, I think you'll hear a lot more about this in the next talk, which are tidal disruption events, which is when you have a star that's interacting with, not another star, but something that's much, much more massive, like a black hole in the center of a Milky Way. We do find these in time domain surveys today regularly, thanks to optical and X-ray instruments. Here is an artist's animation of what that might look like. You have a star that was unfortunate enough that it, went too close to the black hole. It got disrupted and produced this powerful transient. But if you think of where these things are happening, these are preferentially happening in the centers of extremely dusty regions, the most dusty regions in any galaxy that you see around us. So a question that has been around for quite some time is, are optical and X-ray searches really sensitive to the entire population of TDEs? Because, presumably many of them are dust obscured, and we would only see them in the infrared. So it turns out that when you take this sample of Weiss transients and just look outside the galactic plane where all of the galaxies are, then you do find examples of these extremely luminous infrared flares that have gone off in nearby galaxies. Here is an example of what appears to be the nearest tidal disruption event in the last decade that has no optical signatures. It brightens by a factor of a few thousand in the mid-infrared. That's how bright it is. It's a galaxy that's only 40 megaparsecs away. And we now, it has, on other wavelengths, it has like X-ray, maybe radio signatures, and we now have this full sample of events that all appear to be TDEs that have gone off in the last decade in nearby galaxies without showing any optical counterparts at all. So, just to summarize, the WISE dataset has been quite fun to work with. It's a really exciting dataset when you start subtracting images and finding transients. We are working very hard. There are more than a dozen different projects and scientific directions that this project is taking. So if you have an idea for cross-matching this with any dataset, if you want to do have an idea for mid-infrared transients, then please get in touch with us. We're very much looking forward to using this dataset for all kinds of scientific applications. Thank you.
We have time for maybe one or two quick questions.
If it's not scooping anything from Tom's talk, can you comment quickly on observing the potential of observing TDEs from IMBHs? So in that mass regime, and whether the infrared is really good for that or other instruments are better.
Right. Yeah, I think the IMBH game has been primarily discussed in the context of white dwarf TDEs in this. And my general impression is that IMBHs would reside in typically dwarf galaxies, and those tend to be not so dusty from what I understand. So perhaps that is a better optical or X-ray game, I would guess. That's my guess. But I guess the infrared really helps when you're looking at extremely dusty environments in the centers of massive galaxies. That's my first order guess.
First, are there any questions online? Okay.
I'm just wondering how you weed out all the more normal.
Is that working?
Yeah.
Is that good? More.
Okay.
Thomas, is that okay online? Great, thank you. Okay, our next speaker is Tom Hollin, who is a third-year Einstein Fellow at Carnegie Observatory. So, Tom, take it away.
Thanks. I'm Tom Hollin. I'm technically a second year for 2 more weeks. But I'm going into my 3rd year at Carnegie. I'm also a member of the All-Sky Automated Survey for Supernovae, or SASN, and I primarily work on the observational study of transients and primarily tidal disruption events, or TDEs. Just briefly, I want to say thanks to the NHFP and TESS GI programs for funding this work. Today I'm going to be talking about a lot of work that we're doing with TESS, and also want to just highlight Jason Hinkle and Anna Payne. These are 2 grad students who have been leading a lot of the work I'm going to be talking about today. Okay, so tidal disruption events. I'm going to start with just a quick overview. We just got one, so I won't spend too much time on it. But basically, the picture here is you've got a star going around a supermassive black hole, gets too close, and it gets torn apart. About half of that material is ejected, and about half remains bound to the black hole, falls back onto it, and creates an accretion disk, as you can see in this little cartoon here from an early paper. We expect the disk to be quite a TDE. We can learn things about the black hole at the center of it, right? So things like the mass, the spin, and things like that can be studied. They can occur around any supermassive black hole with a mass less than about 10 to the 8th solar masses. So unlike AGNs, which are only a fraction of galaxies as supermassive black holes, TDEs can occur in any galaxy. And they allow us to see the accretion flow form and evolve in real time. So it's something that you can't see in a more stable system like an AGN. So we can use these to study accretion physics in novel ways. But we still have some gaps in our observations, primarily at very early times when a lot of interesting things can be happening. And partly because of this, we just do not fully understand the physical processes that are producing the emission that we see. In particular, talking about this UV optical question, why are we seeing these and not X-ray transients? There's 2 leading theories. One is that, where does TESS come in? Why is this satellite that's designed for studying exoplanets potentially helpful here? Well, as I mentioned, early time data can be really helpful in illuminating the physics of transients. And by early time here, I'm talking about really the first few days and going all the way up to peak light. So just for an example, in type 1a supernovae, in the first couple of days after the explosion, you might see a flux excess. And if you do, that could be a signature that there's a non-degenerate companion star to that supernova, right? So we think early observations of TDEs could